Hello everyone, this is Eddie Britt and I'm going to work on your Test 3 review. I'm going to try to get through as many of these problems as possible in this first video, and we'll just see at the end. I'll let you know if we don't get through them all. Test 3, if you haven't noticed, the calculations, the actual math is starting to come out a little bit more. Have them do a little more calculations, have them do a little bit more probably calculator work. I'd suggest getting a scientific calculator at least if you do get a TIE 3 or 84. They do a little bit more, but I usually don't teach students how to do that unless they ask. So I can help you with something if you need me to help you with it or try to figure out how to do it on your calculator. But everything that we do, we should be able to do just with a Windows calculator. So I'm not going to work out every problem. I may refer back to other problems if we get to something that we have to work out a problem similarly as another problem. Then I'll just refer back to a previous problem. Alright, starting with number 1. The table to the right lists probabilities for the corresponding numbers of girls in 3 births. What is the random variable? What are its possible values? And are its values numerical? The random variable is going to be here. Okay, the number of girls, X. This would be like the number of girls in 3 births. So it says if you have 3 births, you have a 0 and you have 0 girls, that's a 0.125% or 12.5% chance that happens. One girl, exactly one girl, would be 0.375. Exactly 2 girls would be 0.375. And 3 girls out of 3 births, 0.125. All of these probabilities do have to add up to 1. So you can check and make sure that is a probability distribution. But the problem just wanted to know what is the random variable. It's these numbers here, 0, 1, 2, 3. The number of girls, X, that's the random variable. And that's what the choice says here. The random variable is X, which is the number of girls in 3 births. The possible values of X are 0, 1, 2, 3. The values of the random variable are numerical. Problem number 2. We have this table here. It says 5 males with a particular genetic disorder have 1 child each. The random variable X is the number of children among the 5 who inherit the genetic disorder. Determine whether the table describes a probability distribution. If it does, find the mean and standard deviation. So what we want to do is make sure that this table does describe a probability distribution. So we need to add up all the probabilities here. And when you add up all these probabilities, you should get 1. I'm not going to do that because it is a probability distribution, but you could do that in your calculator. Just add each probability up and you should get 1. Now, to find the mean of the probability distribution, we want to see the mean of a probability distribution is the sum of X times P of X. So what that means is you take the random variable X and you multiply it times the probability. Do that for each one of these and then add them all up, the sum. So our mean is going to be equal to 0 times 0.5584 plus 1 times 0.3451 plus 2 times 0.0853 plus 3 times 0.0105 plus 4 times 0.0007 plus 5 times 0.0000. So if you add all of those up, you should get, I believe, it's 0.55. May want to double check my calculations. And if we come down here, it says mean, round to 1 decimal place is needed. So 1 decimal place, if you rounded 0.55, would be 0.6. Alright, standard deviation. Find the standard deviation of the random variable x. The formula for standard deviation of a probability distribution is the square root of the sum of x squared times p of x. So not x times p of x, not this, but x squared times p of x. And then we have minus the mean squared. Alright, so we want to find this value, the sum of x squared times p of x. Then you want to subtract the mean squared. After you do that, don't forget, take the square root. Now, make sure that whenever you plug in your mean, you don't plug in the 0.6, because that's a rounded value. You say, well, the mean's 0.6. Well, that's the rounded mean. You want to put in as an exact value as possible. So, whenever I plug this value in, I want to make sure I put in 0.55 and not 0.6. Make sure that if you ever use formulas, and this goes for any class, you never put rounded values into formulas. It creates a margin of error, and then there's going to be a bigger margin of error after you work the problem. And then if you use that formula for something, there'll be a bigger margin of error. So always plug in as exact as possible. Now, if you have like 15 decimal places on a number, you could probably get away with taking about 8 of them or so, 7 or 8, and rounding there. So it just really depends on the situation and the problem. But I would never take a rounded value like 0.6 and just blindly plug that into a formula. Alright, getting back to this problem. We need to find the sum of x squared times p of x. So we want to say, and we say, where's the x squared come from? It comes from this table right here. We have, when x is 0, there's a probability. So x squared times p of x. So we make a column for those. That's going to be 0 squared times 0.5584 and 1 squared times 0.3451, 2 squared times 0.0853, 3 squared times 0.0105, 4 squared times 0.0007, and 5 squared times 0.0000. Now make sure that you square each of those numbers first before you multiply. And what you'll want to do is find the sum of all of those. You can do that with any calculator. When I'm using the Windows calculator, I usually try to use the scientific mode, because I can put parentheses in it and it'll kind of show me what I'm doing up here in the calculator. So watch this. 0 squared times 0.5584 plus, see, it shows you 0 squared times 0.5584 plus 1 squared times 0.3451 plus 3 squared times 0.0105 plus 4 squared times 0.0007 plus 5 squared times 0.0000. Alright, and so that's going to give us, we add all those up, that gives us the sum of all of those. So the sum of x squared times p of x is going to be equal to the 0.4508. That's an exact value, that's no rounded value. Alright, so for our standard deviation, we're going to have the square root of 0.4508 minus the mean up here, squared. Don't forget to square that. So it's going to be 0.55 squared. And we want to do all this work under the radical first, and then we'll take the square root. 0.4508 minus 0.55 squared equals, now let me make sure that I plug that in correctly. 0.4508 minus 0.55 squared equals. Alright, and so we want to take the square root of that. And square root button's right up here. Sometimes it's kind of hard to find. It's right above the percentage. Alright, so I did stop my video for just a second because whenever I was working all of this out under here, I believe I mistyped something in the calculator. This first number was supposed to be something a lot larger because I can tell, I mean, I have 0.3451 just from this one term, and that's only 0.4508, so I did mess up. I think I messed up punching in one of these numbers. So since I did that, I'm going to redo it. So no extra charge. Let's see, 0.3451 times 1 squared. And you can put the 1 before or after. Plus 4 times 0.0853. Plus 9 times 0.0105 plus 16 times 0.0007 plus, well, there's really nothing else because when you say 25 times 0.0000, that's going to be 0. So that's what we get where I have this written down 0.4508. I should have 0.792. So I'm going to correct that. Apologize for that. Alright, and then we need to subtract 0.55 squared, so minus 0.55 squared equals, and we should have now the square root of 0.4895. Take the square root of that, and when you take the square root of that, you get 0.6996427, so on and so forth. I'm going to approximate that. I'm going to bring it out a couple digits. Okay, it's about 0.6996427. Alright, my problem here says to round to 1 decimal place. So if I round this to 1 decimal place, that'll be 0.7. The next problem, we want to know, does the table, or is the table a probability distribution? So what you need to do is you need to add up all of these probabilities. They should all add up to be 1. If they're not, it's not a probability distribution. But I can see here the answer is yes. So that is a probability, or does represent a probability distribution. And it says if it's a probability distribution, what is its mean? So To find the mean, this is problem number 3. The mean is going to be 0 times 0.05. Where am I getting this from? I'm getting this from the table here. 0 times 0.05 plus, excuse me, 1 times 0.11 plus 2 times 0.33 plus 3 times 0.28 plus 4 times 0.13 plus 5 times 0.10. Alright, so you need to punch that in your calculator. When you do, you should get out 2.63. That is the exact mean. In here, you want us to round to the nearest tenth, so that'd be 2.6. Now, to find the standard deviation, we do need to use the mean, so make sure you use 2.63 and not just 2.6. So that's going to be the square root of. Now, remember this first number here, or this first value, is the sum of x squared times p of x. You got to be very careful punching that in your calculator. And then you want to subtract the mean squared. Then after you do all that, take the square root of it, and that'll give you the standard deviation. So I'm just going to go ahead and tell you what this value is supposed to be. I worked it out in advance. Whenever you make sure you say x squared times p of x for each value, for each item. Alright, and you should get 8.53. So 8.53 minus 2.63 squared. Let's see what that is. 8.53 times 2.63 squared equals 1.6131. So that's what's under your radical. This is all exact. Take square root. Now, you can't write this exact, right? I mean, that's just way too many decimals. I would at least bring it out like 4, 5, 6 places, though. I usually try to bring it out about as many places as I have patience for. So 1.270078. Okay, I'll stop there. So your test wants you to enter that in and round to the nearest tenth. So that'll be 1.3 if you round to the nearest tenth. Okay. Let's take a look at the next question. Alright. Use the range rule of thumb to identify a range of values containing the usual numbers of girls in 10 births. Alright, so we have 10 births here. The probability of having no girls is 0.005. The probability of having one girl is 0.012. Now this isn't at least 1. Remember, this is exactly 1. This is exactly 2. So these probabilities are for exactly that many. Okay? So, we do have to find the mean and the standard deviation to use that range rule of thumb. So, be careful. Make sure that you are careful punching those values in the calculator because that's a lot of numbers. I actually worked it twice to make sure that I got the right answer when I was working it out. So you might want to do that, write down what you get and then punch it all in again and hopefully get the same answer. If you don't, then you probably need to work it a third time just to make sure. That's the good thing about these tests. They're not timed, so hopefully you block off a few hours that you can work on it. Don't stress yourself out too much. Alright, so we want to find the maximum usual value and the minimum usual value. Remember, the range rule of thumb says that we can say the mean plus 2 times the standard deviation. That'll give us the maximum usual value, and mu minus 2 times the standard deviation will give us the minimum usual value. Alright, so we need, well, I've already worked out the mean and the standard deviation. I did that earlier, not in this video, but on a piece of paper. And I got that the mean was equal to 5.086 approximately, and the standard deviation was equal to 1.69074 approximately. And so if I want to find the maximum usual value, I'll say the mean plus 2 times the standard deviation. So for the maximum usual value, that's going to be 5.086 plus 2 times 1.69074. Let's see what that is. Notice I put that in parentheses. I do that sometimes just to make sure that the calculator understands exactly what I want to do and it's not trying to do something different. Okay. Well, I pushed the equals too many times. The first time that I pushed equals, it did say 8.4 something something. So I'll do that real quick. Alright, so I'm going to say plus 2 times 1.69074. Alright, 8.46748. So 8.467 is about 8.467. If I want to round that to one place, I think that's what the test wants me to do, that'll be 8.5. So the maximum usual value is 8.5. The minimum usual value, we want to say the mean minus 2 times the standard deviation, so it's going to be 5.086 minus 2 times 1.69074. Alright, and so let's see what that gives me. I got 1.70452. Let me double check and make sure that I plugged everything in correctly. Alright, so I'm sure you saw me work that a couple times. I was getting frustrated there. I'm sure some of you do the same thing. I was looking over here and I was seeing 1.6 and I was just going crazy, so I actually stopped my video and I started working out this entire problem again for the third time just to double check, you know. And because it says 1.6, but I'm getting 1.7, then when I mouse over it says correct answers, and it actually will take 1.6, 1.7, so yeah, it does have a little error correction in there if you're off by like a tenth or something. A lot of times it'll give you credit anyway. Alright, so based on the result, is 1 in 10 births an unusually low number of girls? Explain. So 1 in 10 births. So if you had 10 children and you had exactly 1 girl, that's 0.012. Remember, anything that is less than 0.05 is unusual. So that's 1.2%. It's less than 5%, so it's very unusual. Yes, one girl is unusually low number of girls because one is outside the range of usual values. And this is just saying that since this 1 is less than this 1.6, then it could be considered unusual. So let's say, as long as you have more than 1.7 girls, which isn't possible, and less than 8.5 girls, then that'll be usual, but anything out of that range will be unusual. Alright, this problem is exactly like the previous ones that I've worked. This is, you just look at the table, use the formula for the mean, you just say the sum of x times p of x, do that for all of those, add them up, round, and you get 1.4. For the standard deviation, just make sure that you use the correct formula. Standard deviation, we need to make sure that we use this formula here, the summation of x squared times p of x minus the mean squared. And when you plug that in, make sure that you do plug in the exact mean that you get. So that is exactly like previously. Alright, I like this problem. This is the probability that if we have 12 jurors from a population in which 80% of the people are Mexican Americans, the random variable x is the number of Mexican Americans on the jury. So this is the probability of getting that, let's say, some fictitious case got Mexican Americans on it, or different juries got Mexican Americans. Now, think about it, though. This says that 80% of the population is Mexican Americans. And this is saying 12 jurors were selected. This is the probability of 0 is 0. It's really not 0, 0, 0, but rounded up to 3 digits. That's what it'll be. 1 is this, and so each one of these are probabilities here. Exactly 7 would be 0.053. This first problem says, find the probability of exactly 8 Mexican Americans among 12 jurors. We just go right here. Exactly 8. 0.133 right there. Now, find the probability of 8 or fewer Mexican Americans among 12 jurors. 8 or fewer means that we want to take the probability for 8 plus 7 plus 6 plus 5 plus 4, so on and so forth. So 8 or fewer, we add the probability of 8 plus the probability of 7 plus the probability of 6 plus the probability of 5 plus the probability of 4. The rest of these are rounded to zeros, so that's where we would stop. Okay, so our probability of 8 or fewer is going to be 0.206. Alright. Which probability is relevant for determining whether 8 jurors among 12 is unusually low? Well, I can go ahead and tell you, if there's 80% Mexican Americans, and the probability of there being 8 of the 12 is only 0.2, I mean, that seems extremely low. And it wants to know which one of these should we consider, the probability of just 8 or the probability of 8 or fewer. And of course, if we were wanting to determine if it is unusually low, 8 or fewer would tell us, would be the bigger of the two probabilities, but that would tell us whether we had an unusual amount of Mexican Americans on the jury. And it says, does 8 Mexican Americans among 12 jurors suggest that the selection process discriminates against Mexican Americans? Why or why not? I would say yes. I would say no, because the probability of having 8 out of the 12 is about 20%. So if this was less than 5%, you could say it was unusual, but no, there's a greater probability than 0.05 of it occurring. It still seems like a pretty low number to me, though. I know I said yes at first, but I guess yes using maybe common sense, but using math sense, where we have to think about that 5% as the percentage that kind of separates usual from unusual, then in a math sense or a statistics sense, we have to say no, because the probability is greater than 5%. Alright, this is an expected value problem. In the state's Pick 3 lottery game, you pay $1.28 to select a sequence of 3 digits from 0 to 9. So you have 10 choices for the first digit, 0 to 9. You have 10 choices for the second digit, 0 to 9. And you have 10 choices for the third digit, 0 to 9. So you have a grand total of 1,000 different choices. If you select the same sequence of 3 digits that are drawn, you win and collect $451.87. It's kind of weird that you're paying in $1.28. It's kind of weird that you're getting out $451.87. But it seems like a pretty good bet. Well, let's see if we did this bet over the course of time, how much money would we win, or how much money would we lose? Let's see. Alright. How many different possible selections are possible? Or how many selections are possible? 1,000. What is the probability of winning? Well, you're going to win if you get the exact same number that is drawn. And so that would be 1 out of 1,000. That's your chances. That's the probability of winning. So maybe I should denote this. Probability of win. Put a W there. If you win, what is your net profit? Well, net profit is, okay, so if you pay $1.28 and you win a total of $451.87, well, you didn't really win $451.87 because you gave them $1.28 just to play the game. Okay, so to find that net profit, you take what you would win and you subtract what you paid in. Okay, and when you do that, that's going to be $450.59. Alright, the expected value. The formula for the expected value is the sum of x times p of x. Now we have two different cases. Either we're going to win or we're going to lose. Alright, if we win, what are we winning? We win $450.59. And what is the probability of us winning? That would be 1 out of 1,000, or 0.001. Alright, so we can figure out our x times p of x by simply multiplying those two together. And if you do that, you should get about 0.45059, something like that. Alright, now what about losing? If we lose, what do we lose? We lose $1.28. Well, if we lose $1.28, I want to make that a negative. So, if we lose $1.28, what's the probability of us losing that $1.28? Well, we're going to lose 999 out of 1,000 times. 0.999. Alright, so multiply those together, and that'll give you negative 1.27872. Now, if we find the sum of those two, find the sum of x times p of x, this will give us our expected value. So over the course of time, we would lose, this is negative 0.82813. Well, this is cents, so you can round to this digit here. So that's going to be, over the course of time, we would lose 83 cents. So the expected value is 83 cents. This game is going to collect 83 cents from people over time for every $1.28 is spent. Alright. If you bet $1.28 in a certain state's pick 4 game, the expected value is negative 0.83 or negative 83 cents. That's the same as our pick 3. So if a pick 4 has the same expected value as a pick 3, that means we're going to lose the same either way over time. Which bet is better, a $1.28 bet in the pick 3 game or $1.28 bet in the pick 4 game? Well, it's going to be the same. Neither is better because both games have the same expected value. Determine whether the given procedure results in a binomial distribution. If it's not binomial, identify the requirements that are not satisfied. Alright, so binomial distributions start in 5-3, and for a procedure to be a binomial distribution, it has to have a fixed number of trials. The trials must be independent, so the trials can't depend on each other. Each trial must have all outcomes classified into 2 categories, like success and failure, heads and tails, win or lose, live or die. So you have 2 different choices. Okay. Let's look. Randomly selecting 200 students and recording how much they like rap music. So does this meet all 4 of the requirements? I gave you 3. I didn't mention the 4th one. The 4th one is that the probability of its success remains the same in all trials. Okay, so we want to know if selecting 200 and recording how much they like rap music. Well, it wouldn't be if they like it or if they don't like it. That's not what it said. How much they like. So I guess there's going to be more than just I like or I don't like if we want to know how much they like. I mean, they could not like it all, but they could like a little. They could like a lot. And so that's why the answer is no, because there are more than 2 possible outcomes. So out of those 200, you're not going to find students that just like or dislike. Some are going to like it a little, some are going to like it a lot, so there's not it's not the same for everybody, so there's more than 2 possible outcomes. So that will not result in a binomial distribution. All right. 4 cards are selected from a standard 52 card deck without replacement. Okay, so you pick one, and then you don't replace it, so then you'll have 51 left, and you pick another, and then you have 50 left, you pick another, you have 49 left, you pick another, like that. Alright, the number of hearts selected is recorded. Does the probability experiment result in a binomial experiment? Well, aren't the success or failure is going to be like whether you get a heart or whether you don't get a heart? Well, since it's without replacement, the probability of getting a heart or not getting a heart is going to change each time because you're going to have one less card. So it does not meet the requirements. It says no because the trials of the experiment are not independent and the probability success differs from trial to trial. So without replacements, what really messes that one up? Changes the probability of each outcome. All right, number 10, multiple choice questions. Each have 4 possible answers, A, B, C, D, one of which is correct. Assume that you guess the answers to 3 such questions. Use the multiplication rule to find the probability of WCC, where C denotes a correct answer and W denotes a wrong answer. Okay? So what that means is the first time we choose, we get wrong. Okay, what's the probability of getting one of these wrong if it has 4 choices? 3 out of 4. Okay? So, if we're using the multiplication rule, take each one of these trials separately and we multiply them. So, we're going to be wrong 3 out of 4 times and then correct. Well, what's the probability of getting the next problem correct? 1 out of 4. And the probability of getting the next problem correct? 1 out of 4. So multiply, that's going to be 3 over 64. And we can get a decimal. 3 divided by 64. And we got 0.046875. And it wants the exact answer. So make sure you don't round. Type in that exact answer. Now, beginning with wrong, correct. Make a complete list of the different possible arrangements of 2 correct answers and 1 wrong answer and find the probability. Alright, so we have wrong, correct. We want to know the different possibility or possible arrangements of 2 correct answers and 1 wrong. So we could get the first one wrong and the next 2 correct. We could get the first one correct and then the next one wrong and then the last one correct. And there should be one other. Let's see, you could go correct, and then wrong. The probability for these are all going to be the same because you're multiplying. It's just these probabilities will be in different orders. So it's going to be 3 out of 64 each time. And we want to know the probability for each. Okay, that's what I did. The exact. Type in that. Exact. Based on the preceding results, what is the probability of getting exactly 2 correct answers when 3 guesses are made? Alright, so the key to this is, let's see, exactly 2 correct answers. There's 3 different ways to get exactly 2 correct. So since there's 3 different ways to get this probability, you have to take the probability and say it times 3. Alright, so 3 over 64 times 3. And that's 9 over 64. Let's see what that is. It's a decimal. And then type the exact answer. That's exactly what they want. Alright, so I have worked out the first 10 problems. I will make another video as soon as possible and finish these up. Please watch this video and all of the videos in their entirety. And if you have any questions, feel free to email me or call my office at any time.